electric field strength due to a uniformly charged rod. Okay. So case 1, I take a point along the length of the rod. All right. This is the diagram. You have a rod AB whose length is L, and the lambda is the standard symbol for charge per unit length, or dq by dl if you will. Okay. It's also called the linear charge density. Of course, if it's area, it will be the surface charge density. And if it's the volume, it will be called the volume charge density. The volume charge density is sometimes simply referred to as charge density. So whenever somebody has not used the adjective before the word density, by default, it is volume. Otherwise, the examiner will specifically mention linear or superficial or aerial or surface. Got it? So P is the desired point. Agenda. I want to find the electric field due to a rod AB, of course, which is charged, and the charge density is lambda, and the point is R away from the end B. Okay. Take an element dq of length dx. So what is the charge on this dx length? That means what is the value of dq in terms of given parameters? dq will be lambda dx, right? So if dq is lambda dx, find out the electric field due to this dq. Is this dq a point charge? No, sir, it's not a point charge. It's of length dx. A length is not a point. I know that, but that's what the calculus helps you for. Point has no dimension. So what do? Your dx is so small. How small? Very small. How small? Infinitely small. How small? Dangerously small, but not a point. Because if it's a point, I can't help it. But if it's a length, I can make it so small that it's almost a point. This is how the calculus bridges the gap. Okay. So dx is a very small length you chose. dq is a charge on it, lambda dx. What is the distance you chose from point P, which is R away from point B? X. Okay. So dE is k dq by x square. Sir, could I have chosen my x from the end B? Yes, you could have. You could have. But then imagine this. If your x was measured from point B, then what is your distance from point P to this element charge? R plus x. Why would you want a bigger expression in the denominator? Always make sure your expression for dE should be as simple as possible, because keep an eye on the future. You have to eventually integrate it. Keep your integration as simple as possible. Whatever complications are there, we can handle in the limits. Keep the integration simple. So x is the distance. K dq by x square. Perfect. For the entire charge, what is the agenda? I will add all the dE's. Hold on. Are all the dE's in same direction? Yes, they are. Yes, I can go ahead and integrate because they all are in same direction, and now I can add them like numbers. So integration, electric field in totality is integration of dE, which is integration of k lambda dx by x square, because I just put the value of dq in that expression, right? This became k lambda dx by x square. I put the value, k lambda comes out. Integration dx by x square is minus 1 by x. Lower limit r, upper limit r plus l. How is that? R is for B, r plus l is for A. See? Now limit is taking care of my entire rod, and my function is so simple. Instead, I would have rather struggled with a r plus x in the denominator. Don't do that. Keep the integration simple. So if I do that, upper limit minus lower limit, I get minus k lambda 1 upon r plus l minus 1 upon r. You sort out the signs, your electric field comes out to be k lambda l upon r times r plus l. Simple. What is the direction of this electric field? In this positive case of charge, it is pointing away. As the black arrow on the screen shows point P, the net field is in this case, from your point of view, rightwards along the axis. Got it?